I'm Norman Wildberger, and today we're going to talk about arithmetic with fractions, basically the operations of addition and multiplication. So in this series on foundations of mathematics, we've so far introduced the natural numbers, starting 1, 2, 3, and so on. And now we've introduced the fractions. A fraction is an ordered pair, mn, written m/n or m over n, where m and n are just natural numbers. And we'll introduce this notation for that statement. So mn being natural numbers, we'll write it as mn are natural numbers. This symbol stands for R, or is. It's like a European euro sign. It resembles an element sign, except it extends a little bit beyond to distinguish it from that. And num here does not represent a set, but rather a mathematical type. In this foundational series, we are not going to talk about infinite sets, because infinite sets don't really exist. And we're going to adopt the rather more historical point of view that something like the natural numbers is a sequence that unfolds beyond our view, but that we have no right to claim that we can grab all of them and put them all together in a single collection or a single set. So this is not a statement about set theory, it's a statement about mathematical objects being of a certain type. We'll say a lot more about that later on. So I also remind you that fractions come with an important notion of equality, that m over n is equal to k over l, precisely when m times l equals n times k. Now when we establish a notion of equality like this, there is an important logical step that we should make sure about. And that is, suppose that m over n equals k over l. And suppose that k over l also equals p over q. Does it then follow that m over n equals p over q? We certainly want it to be true, and we must check that our notion of equality has this transitive property. So let's do that. This first statement here is the same as ml equals nk. And the second statement is the statement kq equals lp. If we take these two and multiply them together, so we take ml multiplied by kq, that's going to be equal to nk multiplied by lp, which we've written here. And now we examine this and we rearrange it using the associative and commutative laws for multiplication. So we take this m and q and bring them together, and the l and the k together. And over here we bring the n and the p together, and the l and the k together. And then we see that we have a certain multiple of lk equals certain other multiple of lk, and so that multiple nq has to equal that multiple np. And that's equivalent to what we wanted to show. So we've used a basic fact that's worth pointing out, and we've used this fact before on occasion, that if AB equals AC, then we can deduce that B equals C. So a multiple of A equals another multiple of A means that those two multiples have to be the same. Now that we have fractions, we have to define what we mean by the sum of two fractions and the product of two fractions. And to define those things, we're going to go back to our laws for division of natural numbers. So I remind you that A divided by B plus C divided by D can be rewritten using the laws for division that we've established. How? We rewrite A over B as A times D divided by B times D. And we rewrite C divided by D as B times C divided by B times D. The reason why we do that is that now the denominators here are equal. And when the denominators are equal, we can add the two divisions by just adding the numerator. So AD plus BC divided by BD. So that was a law for divisions of natural numbers. And for multiplication, AB times CD equals A times C divided by B times D. That was another law for divisions of natural numbers. So we're going to use those two to define the corresponding operations for fractions. We're going to say that A over B plus C over D equals, by definition, AD plus BC over BD. So exactly the same expression that occurred there. And we're going to say that A over B times C over D is AC over BD. Exactly the same expression that occurred over there. So for example, 2 over 3 plus 5 over 4 is 2 times 4 plus 3 times 5, all of that, over 3 times 4. And that's 8 plus 15, that's 23 over 12. While the product, 2 over 3 times 5 over 4, is 2 times 5 over 3 times 4, 10 over 12. Now, although this could be reduced or replaced with 5 over 6, there's no need to. It's correct as it stands. Now that we've defined the operations of addition and multiplication, we must check that they are well defined. That means that we have to check that our notion of equality behaves well with respect to addition and multiplication. Or more precisely, that if A over B equals A prime over B prime, and C over D equals C prime over D prime, then we must check that the sum of these two equals the sum of these two. In other words, that AD plus BC over BD, which is the sum of these two, equals A prime D prime plus B prime C prime over B prime D prime, which is the sum of those two. And then we have to do the same thing for multiplication. Now what does it mean for these two to be equal? Well, it means that this times this equals this times this, and I've written that out. Now what does it mean for these two to be equal? Well, it just means that those two are equal. So our problem is to go from this and this, those are the assumptions, to proving this one. This is a very important logical step when dealing with fractions, and there's no avoiding it. I'm afraid that many undergraduates and graduate students also have gone through their entire mathematical career without having made this kind of check. So here's a good point to remedy these gaps. Alright, so the answer of course is yes, and how do we do it? We take these two initial starting points and we manipulate them. So we take this one here and we multiply both sides by d prime, the product d times d prime. So there's ab prime times dd prime, and then that equals b times a prime times dd prime. And then we do the same kind of thing with this thing here. We multiply this one on the left by bb prime. So we have that times cd prime and that times dc prime. So those we know from our assumptions. And now what we're going to do is we're going to add this thing, the left side here to the left side here, and then that's going to be equal to the right side here plus the right side here. So I'm just taking this plus this, writing it there, and this plus this, writing it there. And now we stare at this and we rewrite it a little bit. So we ab prime dd prime, we rewrite it as a times d times b prime d prime. We rearrange it. And similarly we rearrange that, and that one, and that one. Once we've done it that way, we see there's a common factor b prime d prime here, and the distributive law allows us to rewrite the left-hand side as ad plus bc all times b prime d prime. And this side here can be rewritten in the same way as bd times this quantity. And then that's exactly what we wanted to show here. So we've gone from the assumptions to what we wanted to show. And notice we haven't used the subtraction yet, which we haven't defined. I'll leave the multiplication check of well-definedness to you as an exercise. So now that we have the definitions of addition and multiplication, we need to check that the laws of arithmetic hold for these operations. It turns out that the laws of arithmetic are exactly the same ones as we've already established for natural numbers. But it's going to be an important task to check that they are actually valid. We'll do that next time. I hope you'll join me. I'm Norman Wahlberger. Thanks for listening.